All right, in this chapter, we're going to be looking at reactions, that very specific ones. They're ones that are going to be in solutions of water, so aqueous solutions. Now, we have quite a few that fit into this category, but fortunately, since we are limiting it to water, it actually simplifies a heck of the complexity that we get in most chemical reactions. All right, we're going to see that most of our chemical reactions that we bother to study, at least in aqueous solutions, can be seen as producing one of these four results if there is an actual chemical reaction. So the first one that we have on there is formation of a solid. That really is precipitate. It would look like you mix two containers of water together and something precipitates out. Now that precipitation is going to vary. Sometimes it's definitely a precipitate. Looks like sand forming, it's going to follow down. Sometimes it might just look like it clouds up. So there's various different solids, various different colors, but that we'll get a chance to see what all that is. Now, the next one's formation of water. From observing it, it's not always obvious on some of these reactions because it really will look like you mix two containers of water and you just increase the volume. What you typically see in addition to production of water is a temperature change, and we'll be talking about that some as well. All right, the next one, forming of gas, that really is just as simple as you mix two chemicals together and you will see bubbles. Now, you might have seen that with a Alka-Seltzer tablet. So plop, plop, fizz, fizz. You drop the little tablets in the water and it bubbles and dissolves the tablets. Well, there's three main components in those tablets. And what you're seeing that's causing the bubbles is there's actually baking soda in there, sodium bicarbonate, and then there's a little bit of citric acid, and that acid reacts with the sodium bicarbonate when they both dissolve, and that causes the carbonate to break down into carbon dioxide. And the last one there, talking about transferring the electrons, that's an interesting one, which we'll get a chance to look at a little bit more detail. Really, what they're focusing on, think about getting something like a piece of metal wet. Well, when metal gets wet, it will eventually be able to react with the oxygen that's in the air and in the water and make iron oxide. Now, there's various different forms of iron oxide. The one I'm going to put here is iron 3 oxide. Now, that just happens because this stable iron turns into this Fe plus 3 by losing electrons, loses 3 of them. That loss of electrons is what actually allows that transfer to occur. Now, fortunately, since we know that, we can take various different protective steps ahead of time. Like your car, we cover it with paint. That helps keep the iron from being exposed. We also various different chemical treatments to the metal before it's painted. So even if your paint chips off, it's still protected. Inside your house, you have a water heater. That metal is relatively unprotected. So what they do in most cases is they put something like zinc or magnesium in there, and it turns out both those two react faster. So zinc will turn into zinc oxide, and magnesium would turn into magnesium oxide long before the iron oxide gets formed. All right, so what we're going to see is most of our chemicals that react when dissolved in water you'll actually see results of one of these four. Now that doesn't mean everything reacts when it dissolves. I mean, just dissolving salt in water, you get salt water, and none of these necessarily happen. It's really when you take that salt water and mix it with other things where you make it one of these other four. Excuse me. All right. We're going to actually look into this, but we got to actually add some terminology first. So we're going to talk about what electrolytes are, at least in the chemistry world. And we've all heard of these in the sports drinks and such. They technically are the same thing, but no one really talks about what they are. All right, so technically, electrolyte is a substance that dissolves in water that can conduct electricity. Now, when we talked about ionic compounds, we talked about cations and anions. It turns out cations and anions. Cations are positively charged species, anions are negatively charged species. Doesn't matter what those ions are, if they are high enough in concentration, they will actually allow a solution to conduct electricity very, very well. That would be strong electrolytes. Now, I have a picture here on this next slide that actually demonstrates what I'm talking about. So, it turns out pure water will not conduct electricity. But if I were to put salt water, so sodium chloride, and just dissolve a little bit of sodium chloride in there, suddenly that water would conduct electricity because electricity can move through those positive and negative ions. And it wouldn't take much salt. I mean, in cooking, we talk about a pinch of salt. That's where you put just enough salt between your thumb and your finger. Technically, assuming this container is large enough, that would be enough salt to get this fully light up. Matter of fact, there is enough in us because we're full of electrolytes that if you had this set up, you'd want to turn the power off first, but then you'd stick your hand down in here and just let it soak there for a minute or two. And when you pulled it out and then reconnected the battery back up, you probably would see that light come on. It's not because your hands are dirty, it's just that we as biological processes are full of electrolytes, and they would just be pulled right out of your skin cells and any surface cells into that water because that's low in concentration of ions. All right, but what we're saying is electrolytes. And we have strong electrolytes and we have weak electrolytes. That's what they're talking about down here. That really talks about how much is dissolved in there. So salt, since it dissolves very, very easily, sodium chloride, any reasonable amount, that's going to be a strong electrolyte. But if we have trace amounts of salt in there, it might be a little bit more like weak. And you would measure that by how bright that bulb gets. All right. When we talk about disassociating, what we're talking about is the fact that the ionic compounds do not exist together once they've gotten to solution. Like I was talking about sodium chloride, potassium chloride is an alternative. Potassium chloride, when it actually dissolves and we actually put that little symbol aqueous, what that really means is there's no potassium chloride at all anywhere in there. There are potassium ions and there are chlorine ions floating around there separately. Now, we will see on chemical reactions, it does get written still like this in some cases. That's simply for convenience, but we do want to recognize if you ever see aqueous ionic compounds, it is really individual ions floating around in there. And it doesn't matter what they are. Potassium chloride is potassium ions and chlorine ions. Copper sulfate is copper ions and sulfate ions. Now, only tricky here, to figure out this was copper 2+, you had to know what that ionic formula was, and since sulfates are always -2, that copper would have to be +2. And do remember, our transition metals can have multiple charge states. And even when we have subscripts necessary, so K2SO4, because you need 2 potassiums to neutralize that -2 on sulfate, that would tell us that we need 2 potassiums to make K2SO4. When that dissolves, it does turn into potassium ions, but there would be 2 of them because that does translate, and then the polyatomic ion does stay together. Now, don't ionize or don't rip apart your polyatomic ions. If you have a polyatomic ion in the ionic structure, it stays as a polyatomic ion in aqueous solution. It doesn't turn into sulfur and oxygens. All right. First type of reaction we're going to look at is going to involve these ionic solutions. And we are going to take 2 ionic solutions, doesn't matter which 2, and we're going to mix them together. It does give us what we're going to call eventually just a double displacement reaction. And that's what this with the A, B, C, and D is actually representing. What they're saying is we have metal A, or I should say cation A and cation C, and then anion B and anion D, and we're swapping. Then A ends up with D, B ends up with C. That's what they're showing here. They're swapping back and forth. That double replacement is just what could happen. Now, down here we have an actual example. I have potassium with iodine and silver with nitrate. So when I replace or do my double replace, I'm going to put the potassium with the nitrate, make KNO3, put the silver with the iodine and make AgI. They're doing a swap with each other. In this particular example, and a lot of the examples we're going to see, one of those two new species is no longer soluble. In this case, it's silver iodide. So what we would have is this actually looks like water. This actually looks like water. So we'd have a beaker of water. We'd have a beaker of water. And let's just pour the first one into the second one. And we'd have a new container, or we'd have this container now with double the volume. But also in addition to this double volume is you're going to see particulates in there. And that is silver iodide. Now, silver iodide is a little yellow powder. It's very, very, very fine. If you know anything about weird weather history, back in the 60s, we researched, I'm going to say bombing, that's appropriate, bombing hurricanes with seeds to cause precipitation to increase. I know that seems like the wrong thing to do for a hurricane, but if you do it out in the ocean, the moisture stays in the water. They didn't have a lot of success there, but they did actually, interestingly enough, their goal was not to learn more about the storms, but they learned a lot more about the storms. They also learned why the seeding with silver iodide didn't work. Turns out they were just, technically it works, but the scale they need to go to change a hurricane is something that's not feasible. But it is nice little yellow powder. It's pretty kind of looking. And it's a very, very, very fine powder. And it still gets used sometimes for seeding clouds, but that may or may not work in certain situations. All right. Interesting. Our goal now, since this is talking about precipitation reactions, is we want to be able to look at our starting components and be able to predict whether or not something is going to precipitate out. Now, interesting, we're not going to get this right all the time. We're just going to learn some of the really basic ones. Like if you notice here, I've had nitrates quite a few times we mentioned, and halogens or group 17s on the periodic table are kind of common. We have a few polyatomic ions that are far more common than others. And because of that, we learn rules to determine out if they dissolve. So our goal here is along this line. We are going to determine which ions are present and do our exchange, so we know what our products are. So that's what we're going to exchange our ions, and then we're going to balance out those charges. So we're going to balance the equation. So we're going to make sure it's all ready. Now, once we've balanced it, we're going to figure out from our new products whether or not something's going to precipitate out. We're going to learn these solubility rules. Now, solubility rules could cover everything. We don't cover a lot. Our table is very simplified. Matter of fact, we're going to omit some things on this. So, and we're going to add one thing to it as well. So we are modifying our table some to clarify some of the stuff we see. All right, so, and we're going to learn them in order because up at the top, these are the most important ones. Because if you notice, it says number one, it says most nitrates are soluble. That really does mean that if you have an ionic compound, so cation and NO3, and it doesn't matter if there's parentheses with a 2, 3, 4. So I'm just going to put an N here. It doesn't matter. As long as it has nitrates, you're going to just immediately say aqueous. So even back on this sample problem, since that was nitrate, we immediately put aqueous. There are no exceptions to that you're going to see in this class. Now, in addition to that, turns out nitrates and acetates do the same thing. So they should have been on this list as well. And they are always soluble for anything that we see in this class. I'm writing acetic. That's like if it's an acid. This should be, acetate. Now, those are always soluble regardless of what they're with. So if you see those, you just write them down with that AQ. And also, if we have sodium, potassium, and actually this is anything in group 1, and NH4, they're also going to be soluble. So along with that, on that sample, since you saw potassium there, and that's in group 1, we would have also had a good reason to write aqueous. There aren't really any exceptions we're going to see to that in this class. All right, the next one has some exceptions. So chlorine salts and all halogens, so anything in group 17, so chlorine, bromine, and iodine, are soluble with just these three exceptions. Oh, excuse me. Silver chloride, lead 2, because that would be a 2 plus charge, and this is mercury 1. Those three mixed with any halogen are going to have a solid next to them. So, and that's what happened in this example. Since it was AgI, which is a halogen, we just know that Ag is one of our exceptions, so we immediately put solid there for it. And the next one's another one that's absolute. Sulfates are pretty much always soluble except for barium, lead, and calcium. And 5, most hydroxide compounds are only slightly soluble. I'm going to actually underline these two because we're not really going to ever actually talk about those because they are slightly soluble. And what I mean by that is you can get them to dissolve completely in enough water, so you won't be left with any residual solid, but they're not super soluble. So what we're mostly going to test you on here is the ones that are either very soluble or not. So we're going to leave these two out because they're right between, they're right on that the edge between the two. So what we're going to say is our soluble hydroxide are the ones that follow rule 2. So if I said 2 said these guys are always soluble, so if I put those with OH, we would expect soluble. So this doesn't really add anything other than it tells us that OH is, for the most part, any exceptions to these are insoluble. And that fits in with 6. So 6 says sulfides, carbonates, and phosphates are only slightly soluble. So we would actually put a solid anytime those are formed. The exception to these guys and that hydroxide are anything group 2. So, for example, if I have, I'm going to come down here because it shows it. So if I were to talk about sodium sulfide, and since that's a -2, I need 2 sodiums. Even though it says down here sulfides are only slightly soluble and that we would want a solid, this is actually aqueous because sodium salts are always aqueous. But as soon as I move over 1 on the periodic table, MgS, magnesium sulfide, because it is just a standard old sulfide, it's none exception. This is a solid. All right, let's look at how we're going to see a question like this. All right, we want to balance an equation that would occur if we mixed potassium nitrate with barium chloride. All right, now even though we know that there is no potassium nitrate and barium chloride floating in the solution, it would actually be potassium ions and nitrate ions. We're not going to write it that way. In this equation, we're going to leave them together because that was what the solution was that we mixed. We're going to separate them we're going to separate them later in this chapter, but right now we're leaving them together. All right, now what we're going to show in our reaction is we're going to swap our metals. So the potassium will end up with the chloride. Potassium is a +1, Cl is a -1, so that just makes KCl. Barium is a +2, nitrate's a -1, so barium nitrate is BaNO3 2. All right, now our next step, we're going to actually balance it. And rather than try to balance the ins and oxygens separately, I'm going to balance it as if it's nitrates. And I'm actually going to start over here because of the nitrates. So I have right now 2 nitrates. So I'm going to come back here and say 2 potassium nitrates. And that's 2 potassiums, gives me 2 potassium chlorides. And that takes care of everything else. All right, now the last thing we have to decide is whether or not either of these precipitate out or if they both stay in solution. Now, we have with nitrate, which was one of our rules, so we're going to come here and very quickly say AQ. And here we see potassium, AQ. Now this is going to be an interesting reaction. We have a solution that looks like water and a solution that looks like water, and we mix it together and we get a solution that looks like water. You won't even see that it doesn't even look like anything occurs when this happens. All right, but sometimes it does. What is that yellow stuff? Let's see if we can figure it out following our solubility rules. Because interesting, it says down here, this is potassium chromate, and chromate wasn't anything I talked about on our solubility rules. So we might not know exactly what the chemical complex is, but we might be able to predict what the solid form is by actually doing our replacement. All right, so we're going to start by swapping our metal. So I'm going to put the potassium with the nitrate and get KNO3. And I'll put the barium with the chromate. That's a +2, and chromate is a -2, so it is just, I need to move my coffee. Barium, nitrate, what am I doing here? That's barium chromate. And no parentheses, +2, -2. All right, balancing it out, I have 2 nitrates, so 2 nitrates. That gives me 2 potassiums, 1 chromate, and we are balanced. All right, so what do we know about solubility rules? What do we know about this stuff? Well, potassium and nitrate are ones that are always assumed to be aqueous, so we would assume that's aqueous. Therefore, that yellowish white stuff must be barium chromate. And it definitely looks like it's forming something, so we say solid. Now, we didn't know anything at all about solubility rules with chromate. We figured that out from that picture or from words and text. It told us something about it. And for anything that's not on our solubility rules table, that's exactly how you figure it out. You actually figure it out based on other clues. All right, let's see if we can figure out this one. So we have an aqueous solution of silver nitrate added to aqueous potassium chloride. And we want to know what solid forms. Now, there's something weird we could do on this that could actually save us some time to a degree. Like, for instance, I happen to remember from my rules that nitrates are always aqueous. So there's no way that's part of a solid that's being formed. And I also know the same thing about potassium. There's no way potassium is part of this white solid because all potassium solid substances are aqueous. That leaves me with silver and chlorine. And that would actually be AgCl. That is this thing right here. Ag is a +1 ion. Cl is a minus ion, so it does give me AgCl. I just got to know, is that one of our exceptions for chlorines? And when we get a little bit more comfortable with rules, we will remember Ag plus is one of our exceptions. So this precipitate, that white precipitate, is silver chloride. All right, what's next? All right, we actually were just showing what we're going to refer to as molecular equations. Now, a molecular equation shows the species together. So potassium chloride and silver nitrate. Now, I want you to remember back a few slides ago, we said it doesn't really exist like that. There is no potassium and chlorine floating around that solution. If it says aqueous, it's actually potassium ions and chlorine ions. Well, the molecular equation keeps them together. The ionic equation, which is right below that, is where it shows them all separated out. And you'll see from that picture, that text there, that's why we typically don't do it. It makes the equation very long. I actually had to change the font size to get it to fit on this. So K plus and Cl get separated, and they have to both say aqueous. So it takes a lot of text to write it out. But it shows something very cool. It actually shows the actual ions and how they're going in there. And it shows the species that go back together as going back together. Now, in our ionic equations, you're going to see species that are always ions. Remember how we had rules that said nitrates were always aqueous and potassiums were always aqueous? They always stay aqueous in ionic equations. They will never be part of anything other than those ions. And we see that we actually will sometimes use what we call net ionic equations, where we remove those always soluble or the spectator ions, the ones that stay ions on both sides of the equation. So right up above here, I have that same equation written again, but you notice how there's potassium on both sides and nitrates on both sides. Down here, we just removed them. So the only thing that really occurred, the only net change was the chlorine ions and the silver ions went away, forming silver chloride. Net ionic equation. So we have that basic precipitation equation rewrote. We could write it as molecular equation, which is the top one right there, which is the most common way of writing it. Ionic equations show everything separated, more like how it really is. And then the net ionic equation show you just the reaction that occurred. There's chlorine ions and silver ions reacted to make silver chloride. All right, let's see if we can come up with that and follow all of our rules on solubility with this wonderful equation. If you notice, I just told you what we mixed. We're going to mix sodium carbonate with iron 3 chloride. So we got to do some planning ahead. So sodium and carbonate. Sodium is a positive 1, carbonate's a -2, so sodium carbonate is Na2CO3. Iron 3, Fe3+, chloride minus is FeCl3. All right, solubility rules. Sodium salts are aqueous. Iron chloride. Chloride had some exceptions, but iron is not one of them. Aqueous. Or we could have just looked right there where they both said aqueous. All right, we are going to do our replacement or our swap. So I'll put the sodium with the chlorine to make just NaCl. And the iron will go with the carbonate. And I would need 2 irons for every 3 carbonates. And balancing wise, I'm going to start with the carbonates because it's my polyatomic ion. Right now I have 3 of these. So I'm going to pop back over here and give me 3 of those. That gives me 6 sodiums. So 6 sodiums. That gives me 6 chlorines. 6 chlorines. That gives me my 2 irons. And the final thing in this molecular equation, I need to decide if these are aqueous or soluble. Sodium chloride, because of that sodium, is aqueous, but carbonate was one we didn't talk about yet. So let's back up to our solubility rules. Most carbonates slightly soluble. So that tells us that it's mostly going to be a solid unless it's with something like sodium or potassium. Solid. All right, that is our molecular equation. To turn this into the complete ionic, I'm going to separate any species that is aqueous. I'm going to have to write a little bit smaller here. So I have those 6 sodiums and 3 carbonates. I have 2 irons, and these are iron 3s, and 6 chlorines. That forms, products now, 6 sodiums and 6 chlorines. And our last thing, since that is a solid, it stays intact. Oh, I dropped my plus up there. That would be the net or the complete ionic. The net ionic, we're going to remove our spectators. And if you look, 6 sodiums, 6 sodiums, 6 chlorines, 6 chlorines, those are your spectators. So my net ionic will just have the iron ions and those carbonate ions. And those will form Fe2CO3, 3. Oh, and solid. Can't forget that. That's very important. So I got on the top, the molecular equation. Middle one is the complete ionic, and the bottom is net ionic. All right. Along with precipitation reactions, we also have just standard old acid-base reactions. We often call these neutralization reactions. And we're going to have oxidation reduction reactions or redox equations. So these are the three major types of reactions we see in aqueous solutions. And we're going to get a chance to look at all three of these and how they distinguish. Now, none of them take as much work as the precipitation reactions because we had to learn solubility rules. These really are kind of just, we're going to learn how to identify them more than anything. All right, so first one are acid and base reactions. We got to define what an acid and a base are, at least in the chemistry world. Now, acids are specifically soluble compounds or things that have dissolved in water that produce H plus as a cation. Doesn't matter what the anion is, but if it produces H plus when it dissolves, it is an acid. Now, in general, when we're talking about acids, you will see them they will be written as just HA. And the reason they write them like that is because the A, the anion, doesn't really matter. It could be like chlorine, it could be sulfate. As long as the H in front of it comes off and dissociates, so as long as it dissolves, it's an acid. Strong acids are just ones that dissolve very easily, and there's really only 6 strong acids we focus on, at least at this point in chemistry. It's those 3, HCl, HBr, and HI, and then the other 6 are part of polyatomic ions. H2SO4, like it listed right up there, HNO3, and the other one is HClO4, perchloric acid. Less common, but it is one of our more common strong acids. Now there are other strong acids, but these are the only ones these are the only ones that are considered common. And all you would see is if we were to write these like this equation up here and add them to water, so that like right now this is written as hydrogen chloride gas, but as soon as that dissolves into water, the HCl separates into H pluses and Cl minuses. Every bit of it does. Our bases are the same type of thing. They're just soluble hydroxides, though. And if you remember our solubility rules, that does mean that most things in group 1, like Na and potassium, are going to be bases. They're going to be strong bases because they dissolve totally. And that is, most of our common strong bases are just anything in group 1 with OH. All right, an acid-base reaction is just where we're going to take one of those acids and a base. Doesn't matter which acid, doesn't matter which base, and they don't need to be strong. So down here in my example, I do have H2SO4, but my base is not one of our strong bases. It's just calcium hydroxide. That will still react. So even though this is one of those that was slightly soluble, if we added too much, there would be a precipitate. It will actually react. So what's going to happen is the H will actually combine with the O and take away the OHs. H and O makes water, and then we'd be left with calcium sulfate, which happens to be soluble. Now, we see this to a degree. It turns out most antacid tablets are actually insoluble in water. So if you get like a Tums tablet, that for the most part would be insoluble in water. But there's so much acid in your stomach that when it gets in your stomach, it breaks down some of the acid and it allows it to dissolve. All right, something that's kind of neat though. All acid-base reactions, all of these we call them neutralization reactions. When the acid reacts with the base, you always get water. And that really is simply because all acids have an H. All of our bases have an OH. H and OH make water. Matter of fact, when I took chemistry way back in high school, I was not allowed to call that water. My chemistry professor made us call it hydrogen hydroxide. And we had to write it as HOH. And it is because it was made by H's and OH. Along with that, the other thing we're going to get is an ionic compound, a salt. In this case, it's calcium sulfate because it's made out of the calcium and sulfate. But if you notice, this is kind of like one of those double replacements. We swap the H, like a cation, with the calcium. They swap places. It just so happens that one of the things we make is always water. Now, that does mean the net ionic equation will always have that in there. You'll always have H pluses and OHs making water. That is a common thread of all neutralization reactions. Now, in the lab, these can be kind of neat because many of these will produce heat. Some of them actually get cold. So just by mixing a strong acid with a strong base or an acid with a base, you typically get a temperature change. All right, let's do an example. I've got hydrobromic acid, and we are going to treat it with aqueous sodium hydroxide. So hydrobromic acid is HBr, but since it's listed as an acid, it's HBr aqueous. And we have sodium hydroxide, NaOH, and it would also be aqueous. All right, and let's just do it like we did on our cations and anions. We're just going to swap the cations. So I'm going to put the H with the OH, and I'm not going to make us write HOH. That's just water. And then Na goes with Vr to make NaBr. All right, and we got one H to every one OH, one Na, one Br. Everything's balanced. All right, so species-wise, since that has sodium with it, we're going to say AQ. Now, water, does it dissolve in water? I know, that's true. It's just a liquid. Water is not ever aqueous in itself. It's just part of itself. All right, that would be our molecular equation, and it is balanced. Let's turn that into a complete ionic. So everything that's aqueous gets separated. H plus aqueous, Br minus aqueous, Na plus aqueous, OH minus aqueous. H2O is a liquid. Na plus is aqueous, and Br minus is aqueous. All right, and then to turn that into our net equation or net ionic, we're just going to drop all of our common spectators. So barium and sodium get dropped. So we have H plus and OH form liquid water. All right. Gas forming reactions really only happen for the most common we're going to see is going to involve carbonates or bicarbonates. Now, to a degree, this particular one could be considered an acid-base equation because it does produce water. It's actually making it because this is actually our acid, and it turns out carbonates act like bases. They don't produce OHs, so we're not going to call it an acid-base reaction yet. We will call it a gas producing because here's something interesting. If we think about this as a swap, you see how the sodium ended up with the Cl? The H ended up with the HCO3. This here is H2CO3. Carbonic acid is not stable though. It falls apart immediately. Used to see it listed as an ingredient on sodas. You read the label and the ingredient, they'd say carbonic acid. Well, probably about a couple decades ago, they started calling that carbonated water because acid's a bad word. So carbonated water doesn't sound as bad, and it's the exact same thing. Matter of fact, that's how carbon dioxide dissolves in water. It just turns into an acid as it does so. But this will actually cause, bubbles to form. So if you mix these together, bubbles will form. This is 5th grade science fair project, the volcanoes. We typically then use vinegar because it's easier to get, but if you were to actually do this with standard baking soda and HCl, it'd do the exact same thing. It might just be a little bit more vigorous. All right, last type of reaction, and we have a lot of slides to cover on this, so this type gets very expansive. It is what we're going to call a redox equation or an oxidation reduction reaction. Now, the term comes from the fact that there will be an exchange of electrons, which is weird because if you look at that equation, I don't have any electrons written anywhere. Where the electrons are is this sodium to turn into this sodium. Even though they're both sodiums, this is an Na plus. To do that, that sodium had to lose an electron. And the Cl technically gained an electron. So we had to have one species lose electron, one species gain the electron for that reaction to happen. That gain and reduction of electrons is the reduction oxidation reaction or oxidation reduction reaction. The metal or atom that loses electron is oxidation. Lose electron, oxidized. The other species that gains the electron is reduced. Gain electron, reduce. Leo says grr. The other way you might have heard is oxidation is loss, reduction is gain. Oil rig. Just help you remember which direction goes which. But what we typically find, the metal is what loses the electron. Non-metals gain electrons. Now there are exceptions to that, but typically those are the rules. If you have a metal and a non-metal on the reaction and they are no longer separated, it is likely a redox equation where the metal lost electrons and the non-metal gained them. All right, so that's what we're going to look at. Most of our redox are simple ones. We have a metal and a non-metal forming an ionic compound. Okay, other types of redox equations are going to have something similar to those. And what we're going to see is something that's all by itself, then it's not. In this case, it's actually oxygen. See how it's just O2? O2 all by itself, the electrons are being evenly shared. It's not a negative charge, it's not a positive charge, it's neutral. It's actually evenly shared between those two oxygens. Over here, the electrons are now being shared with a different molecule, and they're going to actually have a different charge effect. So what we can actually safely say to identify any oxidation reduction reactions is if you have O2 all by itself as a reactant or a product, and it's not on the other side, you have oxidation reduction going on. Because the only way the oxygen actually changes its chemical makeup from O2 pure to anything else with oxygen in it is if those electrons get shared or exchanged. Turns out in both these cases, O2 to go to the other side. So this O is just O. These O's are -2. So both those electrons, both of those atoms gained electrons. Same thing happened here. This is a -2 and that's a -2. So the oxygens had to gain electrons on the opposite side from where the O is. But we're not necessarily going to need to figure out those charges. We just need to recognize it as an oxidation reduction reaction. So anything like a combustion reaction where oxygen is a reactant, since it gets used up in the reaction, that is a redox equation or an oxidation reduction reaction. All right, so how do we classify all of our reactions? Well, we're going to actually do quite a few things just by looking at the examples we've done. So a precipitation reaction is just one of those where we swapped our metals in an ionic solution like this thing down here, and we actually caused one to precipitate out. Acid-base reactions, you're looking for water being created, ideally from HA, an acid, and OH, a base. Double displacement reactions are just where they swapped. These both could be considered double displacement reactions because one of these could form a solid, and if it forms a solid, it's a precipitation reaction. One of these could be water, and therefore it's an acid-base reaction. So both these are actually what we also refer to as double displacement reactions. And the last category we had was our oxidation reduction reactions. We're looking for atoms that are all by themselves. So metals all by themselves or non-metal all by themselves, and they react and form ionic compounds, or oxygen all by itself as a reactant or a product. Turns out anytime you see an element all by itself, so even a weird thing, let's say we have substance A, and we're going to let it react with just pure sulfur. And over here we have whatever that substance is A with sulfur. Since the sulfur was all by itself and then it's not, that would have to be an oxidation reduction reaction. All right, let's try to identify some of these other ones that we're going to see pop up. All right, so previous page, into the first category of aqueous. This is one more aqueous reaction, but I want you to notice something. What says up here it's a single replacement reaction, but what's really going on in these equations? Have something that's all by itself and then it's not. Something that's all by itself and then it's not. Those are redox equations. These are oxidation reduction. But they are a special type of oxidation reduction equation. They are called single replacement reactions, and the reason that is, have zinc all by itself, and then suddenly hydrogen all by itself, aluminum all by itself, and then iron all by itself. The item that's by itself gets replaced with something else. Now it does do something kind of interesting. This first one, it really is taking a piece of zinc, putting in acid, and you get hydrogen gas coming out of it. If you're familiar with blimps and such, the Hindenburg was a giant blimp that could fly across the ocean that burned up and crashed in New York back in the, I want to say, 1920s. It was filled with hydrogen, which is flammable. That's why it burned up so rapidly. You can find interesting movies on YouTube where because the explosion was filmed. It caught fire and burned up in minutes because that was pure hydrogen. Well, it turns out they actually made the hydrogen en route. They just kept stores of acid, and I think it was lead they used because it reacted a little bit more rapidly, and they would make hydrogen if they needed to. So if they leaked some out and they needed more hydrogen, they just generated it on site. And they had enough lead, even when it was landing, that the crash site, if you go and check the soil for lead, there's enough lead still in the ground, and it's basically from that crash. Now the other one's kind of a neat thing. So this is rust and this is aluminum. Over time, if you were to mix those together, the aluminum will get an iron deposit on the outside. It'll be flaky metal on top of it. The iron replaces the aluminum. Be an interesting way of solving a rust issue, in the sense that you cover your rust with aluminum and keep it wet and they swap. It doesn't work nearly that well, but in a chemistry setting, you can see a buildup on it. And it doesn't form solid aluminum or solid iron. This is like flakes of iron. So it's not like you could use it to repair a rust spot in a car. All right, other classifications, other redox equations. So remember how we said O2 by itself and then not is redox? Well, that's definitely true, but it's also a combustion reaction if the O2 is a reactant. So the O2 as a reactant turns into something that has oxygens in there. That is combustion. Doesn't really matter what this is. Doesn't even matter what these guys are. The common species is oxygen. And then the oxygen ends up as part of your products. Now, most general combustion reactions involve a hydrocarbon. Some over here that's made of nothing but carbons and hydrogens. And then your product is CO2 and water. And in your gas tank right now, even if you're running diesel, you have a combination of carbons and hydrogens typically. Up to 30 different components of different ratios of carbons to hydrogens and different ways of putting it together. And then when they burn it with oxygen, most of what comes out is CO2 and water vapor. All right, so our other ways, these are still just redox equations. We're just actually breaking down the numbers to help identify things. So synthesis reactions are any type of reaction where there's just one product. These two listed here happen to be redox equations because I got metal all by itself and then it's not, something all by itself like oxygen and then it's not. These are both redox equations, but the fact that they both only make one product is why we call them synthesis reactions. And opposite of that, see how I just have one reactant? One reactant turning into multiple products. That is a decomposition reaction. So sodium chloride, putting enough energy in it to separate it back into sodium and chlorine. It is a redox equation, but it's also what we call a decomposition reaction. All right, so our summary of these redox equations. We have synthesis, where we make a single product. We have decomposition, where we start with a single reactant. Combustion has oxygen as a reactant, and single replacement, something all by itself, and then something else all by itself. And you'll see these on your test something like so. What type of reaction is that? All of our possibilities. If it was synthesis, you'd have a single product. If it's combustion, it doesn't matter what this is, but you need to have O2, and you got to make something that has O's in it. That's why this one is combustion. Decomposition, single reactant. And single replacement, something by itself, an ionic compound turns into something else all by itself, and another ionic compound. So this is definitely a combustion reaction. And that is typically what we're going to do. We're going to, on the types of reaction, you'll typically just need to identify them. Balancing will be kind of separate, and balancing would be for all types, and just follow the rules to balance them. And all those redox things, we won't necessarily need to figure out exactly what species is being oxidized and reduced yet. So knowing that oxygen gets oxidized here or reduced isn't part of knowing what's going on. As long as you see the oxygen is changing, you know it's a combustion reaction and a redox equation. And that finishes up this chapter.